So I'll hand over the stage to Sahil.
Okay. So, fine. The talk is titled Return of the Spin Qubit. You'll get to know why it's a return and not, a new spin qubit. Basically, the idea behind this talk is to let you guys know how hard it is to make a qubit. And the way in the previous talks, the math people, threw around qubits like they were nothing. We will show how difficult it is to actually do that, and try to show you where the field is at, where it was, and where the money is, kind of. Yeah, for funding, I guess. Yeah. Okay. So yeah, let's proceed. The outline of the talk is as follows. First, I will introduce to you what is the physical qubit. You guys know what like a theoretical qubit is, a two-level system is. That through the previous talk clarified that for you. And I will go into detail on what are the main criteria that people have agreed upon, that these are the 5 required criteria that a physical qubit must have. That is the first section. The second section is on a particular qubit that we'll focus on. This was one of the first proposed qubits in 1997 by Daniel Loss. And it is an electron spin based qubit. And we'll go into more depth about what materials were chosen initially for making that qubit and what materials are being used now. Then we'll focus on silicon based qubits that are the most popular spin based qubits right now. And we'll dive into the sort of condensed matter aspect of quantum dots, where you go into charge transport and so on. And finally, we'll end with what this field looks like in the future, I guess. Where can these forms of qubits scale, and what sort of work can you do as an undergraduate in this field? Yeah. So let's get started. What is a qubit? That's our first part. So a qubit is a two-level system, a two-level quantum system. But for a physical realization of a qubit, you need to have the 7 criteria. I have shortened them down into 4 points. The first one is it has to have well-defined quantum levels that are well separated from leakage state. What does that mean? It means that if you have a two-level system, there should not be any. Your state should be in that Hilbert space. It should not leak out into a higher or larger Hilbert space. That is the first part. The second point is, can be coherently controlled with SU2 operations. SU2 operations are fancy way of saying X gate, Y gate, Z gate. Okay. And the point being, you should have a universal set of gates, that is XYZ and C0 for multiple qubit gates. The third point is they can be initialized and read out in a single shot. This point is usually overlooked, but it is why one of the first implementations of a quantum computer, NMR, was rejected or is rejected. Basically it says that your qubit, when you start doing an operation on it, you should know what state it is in, and the readout should be in single shot. Single shot means one shot you get. If you're taking an ensemble measurement, one shot you get one probability, and so on. One shot you get one measurement, and then over an ensemble you get your probability. The last point is, can be selectively coupled and scaled. Selectively coupled in the sense it should not couple to its environment as much, because that will cause decoherence of the qubit, which basically means that it will lose its information over time, which we don't want. Selectively coupled means that it should couple to other qubits so that you can have multi-qubit operations. And the coupling should be long-ranged should extend over long ranges so that you can scale the qubit architecture. Yeah.
So what do you mean by
leakage? By leakage state. So suppose you have okay, you'll see it in this one only. In the quantum dot, suppose you have your two Zeeman split states. Your leakage states would be your higher orbital states that it leaks into, which you don't want. Basically, if you have your Hamiltonian, for a two-level system, it's 2 by 2 matrix. But leakage states would mean that it's a, say, 8 by 8 matrix with the other elements that are very small. It's the idea. Oh, yeah. Yeah. Okay. So when people first thought of qubit, the first qubit that you would naturally think about, the first two-level system that you would naturally think about if you know any quantum mechanics would be the spin-half system. The spin-half system is like your canonical qubit. It literally matches with the Bloch sphere, if you can say that. So it is kind of the most intuitive two-level system. It is not an artificial atom. You're not creating two levels. You're not making changing some form of two levels to make them separate. It is quite literally a two-level system. It also is helpful that this is a picture of the Stern-Gerlach experiment. If you can sort of visualize it better because you can see that the orientation of the qubit on the Bloch sphere aligns with the spatial orientation in the Stern-Gerlach experiment, which is again nice to visualize. So it's a very convenient, safe model to play with. And one more convenient thing is all fermions are spin-half particles and fermions are everywhere, electrons are everywhere. So using an electron as a single qubit should work. Nuclear spin-half system should also work, but the issue is that the splitting in those levels, the energy splitting in those levels is very small. So let's find out if they did work. Yeah, I'll tell you three of the initial qubits that were proposed. The first one that we'll talk about the most today is Loss DiVincenzo qubit. So this was proposed in 1997, and it basically says that if you electrostatically make a quantum dot. Electrostatically, you'll find out what it means later, but you make a quantum dot. A quantum dot is nothing but a particle in a box, and that is the dumbed down version of it. It's a particle in a box, and you say that you can control the number of particles in the box, and you say that there is one electron in the box. That's the idea. And you say that you can apply certain pulses to it to control the spin of the electron. The electron spin, not the nuclear spin. Yeah, that is a key difference, that you are dealing with the electron spin here. And the two levels here are the Zeeman splitting levels. When you apply a strong magnetic field to the electron, it will split into two. The degenerate orbital level, which will split into two spin states. Yeah. The next one is the Kane qubit. The Kane qubit is quite dead now, but I use it as an example because it was one of the early ones, came out in 98. And it basically uses nuclear spin. The idea is that you have a lattice of silicon, 1D lattice of array of silicon atoms. Silicon atoms, silicon 28 does not have any spin, nuclear spin. So you have an array of those atoms, and in between you dope it with phosphorus 31 atoms that have plus half nuclear spin. And so this is again your simple two-level system, but the issue with this was that the doping process was you cannot put one atom individually side by side. We have not reached there, and plus nuclear spins are in general hard to deal with. So this was kind of abandoned very quickly. The last one that is there is relatively new. It's the singlet triplet qubit. It is very similar to the loss qubit. The idea is that you have two quantum dots, both with one electron in it, and you control the singlet triplet states. So if you have two spin half systems, you control the state, you do addition of angular momentum, and you control one, the lower state is the one with zero angular momentum, and the excited state is the one with the plus one angular momentum. These are quite popular now, but right now people are still divided on if whether the loss one is better or the singlet one is better. So now we'll talk about the loss spin qubit. But before that, you might be wondering how are we actually controlling the qubit once we have confined it into a quantum dot. So basically here you can see that the Hamiltonian for this is H0 minus mu b. What does that mean? When you have a certain Hamiltonian H0, that is the Hamiltonian that it has in the quantum well, that is the quantum dot. That has a certain orbital energy level. That orbital energy level has electrons with the same spin. Electrons with spin. And when you apply a strong magnetic field, that orbital energy level is split into two energy levels. This degeneracy is broken by applying a strong external magnetic field, and its mathematical form is as shown here. The new Hamiltonian is H0 minus mu b. It is like adding a small perturbation, and you can sort of simplify it and write it in terms of the magnetic moment, the magnetic field, and the sigma c matrix. Math really is not important here, but the idea is that
Okay, I found this on the web for you. Here you can see that the Hamiltonian for this is it 0 minus MEBR. What does it mean when you have a certain Hamiltonian?
okay, nice, thank you. Okay, yeah. So the energy difference between the two spin states, spin up and spin down states, is given by this G mu b times the magnetic field strength, and that I am saying it is equal to h bar omega L, where omega L is the sort of Larmor frequency. It will be better if I sort of write this down, because the next part is slightly complicated. So you can think of this as your log sphere, where you have your levels of the qubit, and this would be your zero state, and this would be your one state. And what you do here is that once you split the energy levels using the BZ magnetic field, then the block vector is simply precessing about the z-axis at an angular velocity omega L, which is given by that formula there, where you equate omega s bar omega L to the energy splitting. And why does this happen? Well, the electron spin before you apply the magnetic field is randomly aligned according to whatever thermal agitation is there. And once you apply the magnetic field in whatever orientation it was, it starts precessing about the z-axis, right? And that is your Larmor frequency, and this is called Larmor precession. But you can, this literally just splits the energy level. If you want to control this qubit, you can apply a magnetic field that you control, that you have time dependent control over. So you apply this magnetic field, that is B1 cos omega t in the x direction and B1 sin omega t in the y direction. So that would mean that this is your x, y, and z. You apply, I'm sort of superimposing the spin and the block sphere, which is kind of allowed in spin qubits because, well, they are canonical systems. So when you apply a magnetic field here, the idea is that whatever direction you apply the magnetic field, the block vector will rotate about that axis. That is the idea. So if you apply these time-dependent magnetic fields, you can sort of control how much it rotates by applying a pulse of a particular duration, so that it rotates only by that much amount. And so the magnetic field that I've shown here would just keep it rotating between the 0 and 1 states, right? You just keep rotating between the 0 and 1 states. And that is your Rabi oscillation. These are terms that you will come across if you look into quantum computing. And right. So yeah, the idea, main takeaway is that you can control your spin state, your block vector, by applying certain magnetic fields in certain directions. The Z direction magnetic field is simply for the splitting of the energy levels, and the X and Y ones are for moving it around the block sphere. Right. And so once you have that magnetic field, you can write down this simplified Hamiltonian. And this, if you know somewhat of some quantum mechanics, this you can write as a general spinner rotating in the block sphere.
If what do you mean by precession? How do you identify as actually precession in both fields? Like, initially, how do you determine that?
Okay, there is a classical idea to it because the electron spin has a magnetic moment. If you have a magnetic moment that is in this direction and it is spinning randomly, suppose your block vector was spinning randomly like this, and you apply a magnetic field, it is going to start precessing about it, right? It's going to face the torque, and then you can sort of, it's a semi-classical picture. That's not how it exactly works, but that's the explanation that I'm fine with. So yeah. Where were we?
Can you remove the zoom?
Oh, it's back up. Oh, are there messages? Okay. So yeah, that was about how you would control a spin if you were given one, right? So we're trying to make a spin qubit here. I told you how you would control one if you're given a spin qubit, and how do we house that qubit? To make that electron, isolated, we need to go into some material sciences, and we need to think about 2D electron gases. So this is a bit of a history thing that we'll talk about MOSFETs and 2D electron gases. MOSFETs, we are all science students, so probably not familiar with engineering things, but MOSFETs are, they're transistors, as it says in the name. But they're more important because they led to 2 Nobel Prizes. Quite cool. And that led to some fundamental discoveries like the quantum Hall effect. I'll tell you why. When a MOSFET is in its inversion mode, that is when a MOSFET is basically like this, you have a you have an NPN junction, and you apply a gate voltage here, you apply a source voltage here, and drain voltage here. The idea is that when you apply a negative voltage to the gate, a channel is formed that classically engineers like to call it a channel, that suddenly current starts flowing. But when you look at it on a mesoscopic scale, you see that it's a 2D electron gas. What is a 2D electron gas? It says that when electrons are confined to a thin 2D layer with where their mean free path is quite large, the electrons can behave like a gas. That means you can apply kinetic theory of gases on it. That is the main takeaway. And the other thing is that its de Broglie wavelength is not very large, so that you can say that it is actually confined to the 2 dimensions and does not extend out. Right. So that is a 2D electron gas, and this is formed in the MOSFET, and it was first discovered in the MOSFET in the 60s. And consequently, they are trying to apply a magnetic field to it and discovered the quantum Hall effect, which is used everywhere nowadays. But it is a tangent. Next thing is that, you don't want to, you can't really make a qubit in a MOSFET. There are other reasons for it. It is mainly material reasons, that the silicon oxide is not really good for housing long-term qubits with a large T1. I did not explain T1. I will. I'll do it. It'll come soon. I'll explain what that is. But yeah, 2D electron gases are found for free. Matlab, you don't need to apply any gate voltages to get a 2D electron gas. And you find these in heterostructures. Heterostructures are these kind of sandwich-looking things where you have You have like you have an oxide up there. You have probably can't see this. Basically, it's a junction of two types of semiconductors. One is aluminum gallium arsenide, and the other part is gallium arsenide. So, in this layer, where you have here, you get a 2D electron gas forming. You get one that forms there, and that is because when you have two different semiconductors coming together, the band structure sort of bends, and the way it bends is that it sort of allows you to like localize your particles inside. Like if you can see sideways, this sort of looks like the bound states of Coulomb potential, that's hydrogen atom. So you get this sort of bounded atoms at the interface.
So what is that?
What is what?
What you described? What you described?
This
No, of that. You said you can bound the electron. In what?
bound electrons. So in at the aluminum gap.
You have two semiconductors and you have the space between them, right?
Yeah. And the space between them. So both of these materials have different characteristics, different lattice constant and all that. So because of that, at the boundary, your band has to be continuous, right? That is, energy has to be continuous. So accordingly, your band will bend to make it continuous, because on the other side it is this way, other side is there, the band will bend. And your electrons will be stored, as you can see in this picture. Maybe it's not a very nice picture. I'll draw it sideways in this. You have this sort of potential in the aluminum gallium arsenide region, and this sort of region in the gallium arsenide part. So your electron states can be bound here. This looks like your hydrogen atom wala bound states. So that is where your 2D electron gas is formed, and it is formed for free. You don't need to apply any gate voltage as such. And so you can say you can make quantum dots in 2D electron gases. I've been saying quantum dot a lot, but you guys probably still don't know what it is. We'll find out soon. But let's move on. Wait. Yes. There is no potential there. You don't need for heterostructures, you don't need to apply a potential. It exists for heterostructures. For MOSFET, you need to apply gate voltage. Right. So now we need to think about now you have your 2D electron gas. Like what do we know so far? Laws had proposed that you can confine a qubit, confine an electron in a quantum well. Now we know how to control this electron. We know how to make the well, right? We know how or where to make the well. You can make it in a 2D electron gas. But now we need to choose the material for this substrate that has the 2D electron gas. So for taking that, you need to go into more material science work. Gallium arsenide and aluminum gallium arsenide is one of the most easiest materials to work with after the MOS. And since it was invented in the 80s, 90s, I guess, it has been, its nanofabrication techniques have been thoroughly, investigated. And so they are one of the most easiest materials to work with. And so that has been the workhorse for this spin qubit since the 2000s. And you also have that industry like Intel and all used to use it for transistors. And so, you can borrow their equipment and expertise to make the work go faster. And so what is the issue with gallium arsenide? I told you that silicon is the new king, so-called now. Why is that? Well, gallium arsenide has two big issues. One is that it has a nuclear spin. So nuclear spin, since we are controlling electron spin as our two-level system, nuclear spin from the material will interfere using hyperfine interaction. Hyperfine interaction is basically when if you have your these are your Zeeman splitting levels for the electron. You can have another splitting here, chota wala, because of the nuclear interaction, which you don't want because that will decohere your qubit. So that is the main issue, I guess. Silicon does not have that. Then the next issue is low T1, T2. I will explain what is T1, T2 now. Should have done that before. So this is clear on this. If you have your, say, if you initialize to the 0 state and you apply an X gate and it goes to the 1 state, bit flip. Now you keep it there and you measure after some time T. And you find that your qubit is now back in the 0 state. What has happened? It has thermalized. This is called thermalization constant or relaxation constant. And this basically means that it went from the excited state to the ground state automatically. So this is called your T1. This has a special name. The other constant that you have, because everything that you do, every gate that you apply, you see that all your states have an exponential E by T1 factor. That everything is valid for only this much time. Everything is decaying with this factor. And so you want this to be as large as possible. Right. Next is your T2 time. So what is that? Suppose you have your 0 qubit, you have a 0 state, and you apply a Hadamard to it. Then you get a plus state. You wait some time, and after that, you wait for suppose some time T. And then you apply Hadamard again to whatever state psi is first. You'll find that you might not get 0 all the time. You're supposed to get 0 because Hadamard is 1. But you'll find that you will get 0 or 1. Because in between, when you waited a time T here, this qubit had a phase decoherence, so to say. It went from the 0 plus 1 state to 0 minus. Yeah. And so very rightly, it is called the phasing time. And this is called your T2. And so these are two parameters that we use to measure qubits with. Yes.
What is causing the phasing?
The phasing, coupling with the environment.
But I mean, it's a very, very specific kind of coupling where you're
Yes.
looking from that to that.
Yes.
So I mean, it's very specific.
Mhm.
It doesn't seem like thermal.
It is, yeah, that's why it shows this example to show that it is different from thermalization.
Okay.
Basically, it is saying that, and this does not have to be a minus like a pi phase. It can be any arbitrary phase. And that is because you can have some, like you will see in quantum dot, there's some capacitive coupling is there. If it is slightly changed, your potential will change and accordingly Hamiltonian will change and you'll get some other gate appointment. That's the idea. So this is your T2.
You can write, I mean, with respect to like Rabi oscillation also, there is going to be some kind of decision which still exists, or it doesn't change. Or
No.
can you explain it?
No. Rabi oscillation is thoda different because if you're talking, are you talking about the rotating wave thing?
Right.
That
I'm
is,
just saying the fact that Rabi oscillations need not be just between 0 and 1.
it is up to you.
Could be representing via any.
Yeah, because Rabi oscillation, you're applying a field, right? You're applying a constant changing pulse, right? You're applying some B1 cos omega t minus B2 sin omega t.
Right.
And so it is rotating about some arbitrary axis according to that. Right. But you're supplying power to it, that's why it's rotating. Right. So yeah, these are your T1 and T2. T1 is called the thermalization time, T2 is called the phasing time. Right. So back to the materials. Yeah. So the T1 and T2 times for silicon and germanium. Okay, this graph is not very visible to anyone. Okay, I'll talk about the T1 thing. So T1 time in silicon is around 1 microsecond, and T1 time in aluminum gallium arsenide is much less. It is 0.01 microseconds. So obviously you want longer coherence times for your qubits, and this is one of the reasons. The second reason is that even your T2 is low. Your T2 time is 1 microsecond and 10 nanoseconds. So 10 nanosecond is, you can't really do any gate operations in that time. So it is kind of useless. Next thing is effective mass. So effective mass is a property that arises in solid state physics. Basically, it is that due to the lattice potential, the mass of the electron is reduced or increased or turned negative or whatever, depending on where it is on the band diagram. So there's a formula for it. Your M effective mass is 1 over S per second. It is related to the curvature of your band diagram. But the main takeaway is that the tunneling rate decay between your what do you say, the dot and the path of electrons is proportional to the exponential of the effective mass. And so the larger the effective mass, the more your qubit is susceptible to gate voltages. That is the idea. It is proportional to mass times your gate voltage. And so if M star is large, then okay, can't see it.
But tunneling you mean leakage, basically.
Leakage, and I mean we need tunneling anyway. If you're going to put electrons into the dot, you need tunneling anyway. But yeah, in this context, it is because of leakage. Yeah, it is M star times V. And so the larger your effective mass is, the more it is susceptible to the voltage that you change. So you have again, you have anisotropic effective mass in silicon. So it is different along the x-axis and different along the y, but whatever. On average, it is still much larger than gallium arsenide, which is kind of what you want. You can it is more susceptible to gate voltages. You have more control, and you can tune it more. So one more thing that you can sort of see from this formula. This is like a rudimentary experimentalist approximation. Like you're familiar with your Bohr radius. It is like 4 pi epsilon naught epsilon r. What is it? H square by m star e square. This is your Bohr radius. So you can sort of think of it as the first, the size of the first 1s orbital, right? And if you calculate this for your silicon, electron in the 1D, this one, 2D gas, you find that it is now dependent on the effective mass and the dielectric constant of the material. And so, since silicon has a much larger effective mass than gallium arsenide, you see that this Bohr radius will be much smaller. And so you get the sense that the wave function for the silicon atom will be much smaller. And so, and for the aluminum calcinide, gallium arsenide will be much larger, right? If you look at the spread of the wave function so far. So Well, what does that mean? That for an experimental, it basically means that you're working with 200 nanometers or 100 nanometers. So when you're working with gallium arsenide, you're working with 200 nanometers. You're working with much larger and easier to build fabricated gates. And that is why this was popular again before, because in the 2000s, we did not have the technology to go down to the 100 nanometer scale. And so now that we have that technology, people are moving towards this. But the takeaway is that you need to have much smaller gate sizes, factor of 100. Factor of 2. Sorry. But still, that is still quite a bit to achieve. Right? Yeah. So that is your host materials. So that's why people decided that silicon is a better option to build spin qubits, and gallium arsenide is rejected. And I would say mostly it is because of the nuclear spin that it has. Since silicon has an isotope, silicon 28, that has no spin. And so you can easily have very little hyperfine interaction in your silicon-based spin qubits. Right. So now we'll still look at the qubit in the gallium arsenide quantum dot, because it is sort of the prototype for what will happen in the silicon case. How do you now make the qubit? Now we have all the ingredients together. We have the 2D electron gas. We know how to control the electron with magnetic fields. So now we have everything ready. So you say that if you have your 2D, your quantum dot here with your gate voltages here, these, I'll show you photos in the, yeah, they're there, right? Like you can see in the photo over, is there a pointer? The photo that on the left, the grayer one with one dot on it. That is a single dot qubit. Actually, can I?
What is the dot?
Sorry?
What do you mean by dot?
Oh, it's right. So, dot. That is a well. Okay. Do you understand? Okay, I'll explain that. Sorry. So basically, what you do is, now that you have your 2D electron gas, right? This much, I guess, we are clear with. You have a 2D electron gas. Now, what you can do is you can put electrodes over here. Electrodes over here, electrodes over here, right? And you apply a negative voltage. So once you apply a negative voltage, it's obviously going to push the electrons into some weird shape, and you can pretty much control it to a very high degree of precision, and you can get a quantum dot of whatever shape you design. This is called depleting the 2D electron gas. You're applying a negative voltage here. So this region will have no electrons essentially, and all of them will be concentrated here. And so now to remove if there are like some 100 electrons here, you want only one. You can have other gates. These are like, suppose these are used to define a dot. Then you can have other gates like plunger gates that slowly couple out electrons via changing the voltage. So this is how you make the dot, and this is now your classical particle in a box. They're literally a particle in a box, except that you don't have an infinite square. Well, it's a relatively finite square. But you can still use the Hamiltonian for that over here, kind of. We'll come to that. You can do that by these gate voltages. We'll come to that.
You can't talk about the levels.
The energy levels of the dot.
Because if you're saying it's a particle in a box, then you'll have
Orbital energy levels. Sorry?
you'll have equals. You're not actually now.
Yeah, it will have orbital energy levels, but in the end, you're going to use it can be anyone. You don't even need to use the ground state orbital. You can use first excited state as long as you have.
People say that a particle in the box has equal space,
Hmm.
but they're not equal space.
Right.
And
Right. Okay, so right, the lost qubit can be realized by applying external magnetic fields. Before that, I should have mentioned the negative top voltage thing. So this is the sort of side picture. The cross section picture is something like this. Yes. So I told you about the infrastructure here. You have your relevant there only, al gas and gas. And here you have your 2D electron gas filter. Right, this is your heterostructure. You put your top gate. These are called top gates. The things that you see here, these lines, they're called top gates because you put them at the top of the heterostructure, and they sort of embed through here by some sort of osmotic fashion. I really don't know how they go through, but this metal somehow makes it through here, and it makes opaque contacts here, and that's how you sort of control the potential of the 2D electron gas, and you can make your dot. So that is what a top gate is, and that's how you made your quantum dot. Now that you made your quantum dot, you can apply a magnetic field to it, and you get your Siemens splitting levels. But I still haven't told you how to get one electron here. Right now, you don't know how many electrons are there. Get to that.
So dot is the potential.
Dot is the potential. Elaborate, thoda.
I mean, like, you have allowed the electrons to move into the certain place. So that place is called the dot.
The place is called the dot. Yes.
So it's not a single electron with this side.
No. The electron is confined in the dot. That's the key point, right? Which is kind of strange because dot is supposed to be a 0D object, but you call it a circular object. But that's the terminology they've used. Yeah, and the number of electrons, like I mentioned here, are controlled using plunger gates. I mean, I'll try to get the pointer thing working. Okay, can you see the? Okay, yeah, perfect. So this is a single quantum dot, right? Here, these two are your gate defining voltages, and this one is your quantum point contact. I will tell you what that is later. And this one is your plunger gate. So the two on the side control the quantum dot potential. It forms the quantum dot, while the one in the middle over here, that is the one that supplies or removes electrons from the quantum dot. These are again metal electrodes only. And this one is a quantum point contact. I'll give you a brief idea about what it is. It is basically a device when an electron tunnels around it, it will tell you that there is a current. That's the idea. It's basically kind of like a transistor only, single electron transistor. It can measure single electron tunneling events. That is one of the coolest things that I've seen. A single electron tunnels across the quantum dot, and it will show a spike in conductance on your graph, which we'll talk about soon. But yeah. And the next picture is a double quantum dot. So again, these are your gate defining voltages. This one and this one. This one is again, I think, plunger gate. These two are single electron transistors, also known as quantum point. They're single electron transistors and quantum point contacts are very similar in their working. So you can use them interchangeably, kind of. So here they've used QPCs, and these will measure the current when an electron tunnels out of the dot or the electron tunnels into the other dot, whatever. You can measure all of that using these QPCs. So that's and again, you can see the scale. This is a 200 nanometer thing. It is in gallium arsenide. Yeah. And so, yeah, the next picture is the sort of side view that I drawn here, kind of. You can see that the top gates are not touching this one 2D electron gas exactly. It is just above it. And whatever electron transport is happening is through tunneling. And yeah, that's the picture below that is supposed to be, I think, 4 quantum dots. You can make a lot of these, but then you don't really have much control over them as you scale. So yeah, that's it for gallium arsenide. Now we'll move to the main guy, which is silicon. So yeah, silicon germanium qubit. So this means that your heterostructure is slightly changed. It's now silicon germanium, and silicon, and you have your 2D electron gas forming between the silicon germanium and silicon interface. Right. So I'm not going to go into how they are like constructed. It is very similar to gallium arsenide. The pictures that you saw before of the quantum dots, it is essentially the same, but at 100 nanometer scale. So not going to bore you with those pictures. We'll go to charge transport in the quantum dots. So that's how you know how are you changing number of electrons in the dot, right? So why can you actually, when I supply a voltage, why am I able to change the number of electrons here? That is because these electrodes are all capacitively coupled to the quantum dot. There is a capacitance over here, C1, C2, C3, so on, so on, so on. Right? Your classical capacitance only. And there's also voltage associated with this. So you can have you can calculate the energy of the dot with this. You can have your CV squared for a term. And accordingly, suppose you find the energy of a quantum dot with n electrons, and subtract from it the energy of a quantum dot with n minus 1 electrons in it. This is defined as the electrochemical potential mu n. And since you will see that the energy will be dependent on the voltage, gate voltage squared, you don't really want to use that for learning about the system, because square is kind of inconvenient to deal with. So they invented this thing, chemical potential, which when you subtract these two, you get something that is linear in the gate voltage. And so you can see how the chemical potential changes linearly with the gate voltage. That you can see in this formula, ugliest formula that is given here. But it provides a nice visual picture about what's happening. So if you have a single quantum dot, say you have your what's here. This is your source voltage Vs. This is your drain voltage Vd, and this is your gate voltage Vg. Right. This is your single quantum dot, and if you're trying to now see how many electrons are in this quantum dot, you can sort of visualize it this way. You can plot its chemical potential. You can say that suppose it's the quantum dot's chemical potential is mu of n over here, and that of the source drain voltage is over here. So the mu n state is the terminology that they use is it is beyond the window of the source drain bias. And so once you increase the source drain bias, increase the voltage here, you'll see that this will essentially come down and this will enter this window here. This basically means that now it has n electrons. Before it had n minus 1 electrons. And so accordingly, you can slowly deplete the dot, and you can go to 0 electrons, you can go to 1 electrons, as much as you wish. And one of the best things about this is that there is something called a Coulomb blockade that forms, again in some technical way, that if you are not in this region, if you are not in the window over here between source and drain, then there will be no electron transfer. If you keep 1 electron there, and that state is suppose out over here, it is not going to automatically come here unless you change this gate voltage. So the number of electrons that you keep in your dot are very precisely controlled and will not change over time. That is something that you want. Unless you can, like, the only changing will be the tunneling thing that I talk about, the mass wala thing that I talk about. But those are again on the time scales for your gates, they are not really relevant. So yeah. And so that is how, and experimentally you can kind of see this. This is a very cool measurement that when you have this, suppose you have a charge sensor over here, QPC. This is your quantum point contact. And whenever an electron tunnels through here, this will show like a delta function type peak in the conductance. Because immediately there was an electron going through, so the conductance is di by dt. all the measurements that we take in the transport here are di by dv measurements. You don't really take current measurements as such. The reason for that is that the conductance is proportional to the tunneling probability or the tunneling rate. And so that is why we use the differential conductance measurements. And so as you can see in the plot here, it plots the I dot versus the gate voltage VG. And every time you add you increase the gate voltage, some electron gets added to the dot, and you can see one peak in this one differential conductance. And you can obviously see that if you take the difference between those two peaks, that is your addition energy, the amount of energy it takes to add an electron. So yeah. This is called the Coulomb blockade. Again, that if you're not in the window here, if your chemical potential is out of the source drain window, then there will be the number of electrons in your dots will remain the same. Right, now to the kind of fun part. This is qubit control with RF pulses and a hint of double quantum dots. So now that we have our dots, we know how to control the number of electrons in the dots. So we have put one electron in the dot, we have put magnetic field. Only thing left to do now is operations on it. And that you can kind of do with RF pulses. So as you can see, when you draw the quantum dot again, suppose you have a single quantum dot, you have your source, drain, and then gate. You have some quantum to quantum here. The idea is that across this there is a so-called antenna, where when you supply a certain radio frequency pulse to it, it will generate a magnetic field, which will then, according to your right hand rule or whatever, it will it will interact with the spin and cause the shifting on the Bloch sphere that we talked about earlier when we talked about electron spin resonance. And these pulses are made using a vector signal generator. And the idea is that you need to send pulses. So you need to send, you cannot send a continuous wave, otherwise it will keep spinning on the Bloch sphere. So instead you send a pulse of a particular time tau, such that this corresponds to the amount of time it takes to go from 0 to 1 or 0 to whatever you want. And so these pulse designing is another big component of quantum computing and all. It is there in superconducting as well. And so this is how you control your qubit. You send these RF pulses that are modulated using a arbitrary waveform generator. And arbitrary waveform generator, it basically does something called, too many technical words, but it does something called IQ modulation. IQ modulation, basically what it does is that it will, when you send in your RF pulse, which is your microwave or the main frequency that corresponds with the rotation here, when you send that in, it will send one pulse that is in phase with it and one pulse that is 90-degree offset. So one sine component, one cos component. And the sine, the cos component will act as the X gate and the sine component will act as the Y gate. That is the sort of, because you're providing those magnetic fields, right? Sine wala and cos wala, which we saw earlier in the electron spin resonance, that the cos wala is the X rotation, sine wala is the Y rotation. Right. So yeah, the device has antennas that convert the RF electrical signals into a magnetic field, time-dependent magnetic field, which then changes the qubit along the Bloch sphere. But sometimes this electric field is, the magnetic field is not strong enough. So they add micromagnets around the device along the substrate. They add micromagnets to strengthen the magnetic field. I don't know how they work, but I hope I find out soon. The next part is a double quantum dot. Double quantum dots I'm really only mentioning them because they are used for the singlet triplet qubit. And basically, if you have one dot here, one dot here, then you can sort of change these two vertices, V1 and V2, right? And you can plot V1 versus V2 to sort of map whatever electron number combinations that two dots can have. So when you sweep these two voltages, you sweep V1 from 0 to 5 volts, you sweep V2 from 0 to 5 volts, rather 0 to -5, 0 to -5, and you take a differential conductance measurement. You'll get this very pretty diagram. This is again, this is called a charge stability diagram. It is the hexagon, and it basically tells you how many qubits are in, how many electrons are in which dot. So the bottom left part has 0, 0. So both dots are empty. And as you pulse along either of the gate voltages, you can get to the other level, like 1, 1 or 1, 2 or so on, whatever you wish. And this is how you control a singlet triplet qubit. You go to the 1, 1 state and then you do whatever. But yeah, that is finally you have readout. Readout is measurement, basically. Measurement, I can explain in a relatively similar way, I guess. There are a lot of ways to measure. I have chosen this one because it is the most easiest to understand. Basically, when you have your splitting of the energy levels, you'll have that the plus wala mu is here, right? Mu n of the higher spin state is here, and of the lower spin state is here. And your source state is somewhere here. Mu s and mu b. So as you move the source state up, you'll see that if the electron, after performing some gates on it, suppose you perform the X gate on it and then you measure it, if it is in the it did get flipped from the 1 state to the 0 state, then it will immediately show a current in the QPC because it has crossed the window, right? But if it was in this state, then it will not show current because it has not crossed the window. That's the basic idea. You change the source and voltage slightly, and you find that if you find a current, then it is in the higher state. If you don't, then it's in the lower state. That is your readout, Elzamian readout, so called. And yeah, that is kind of it, I guess. Last is the scaling for this qubit. I'll talk about the sort of quantum stack first, then we'll go to scaling. Because this is something that a lot of people want to know what to do in quantum computing. So first, on the ground level, like this is telling you what you can do in the quantum computing field. At the bottom level, there is the quantum plane where you see where you deal with the hardware, the quantum hardware, like the dots and so on. The next layer is the control layer where you deal with mostly the electronics, like what gate voltage you're supplying, what electronics you're using. The next part is the control logic, where you see what sequence of electronic you need to apply to efficiently do your work. Then you go to architecture, which says key, how do you do this on a larger scale? Then framework, then algorithms and applications. So the idea really is that there are a lot of things that you can go into. Like people, if you're into algorithms, then you'll be very disconnected from the hardware. You can really approach any of them according to you. And yeah, so this talk was mainly about the control and the last two plates, I guess. But yeah. Again, this is about the scaling. So that was the last DiVincenzo criteria that we had to satisfy. Everything else we've satisfied so far. Scaling, there are two ways to sort of do it. One way is that suppose you have your quantum dot here with your electron, you couple it to another one using another quantum dot. So you just keep doing an array of quantum dot to slowly transfer your state from there to here. The actual DiVincenzo criteria is that you need to have flying qubits. Flying basically means that you should be able to transfer your information across the quantum computer physically. The quantum dot method is quite shit. It does not really, because you lose information across every dot. So what has become popular now is like coupling the spin state of the quantum dot, of the electron in the quantum dot, with a resonator, a microwave resonator, which is a superconducting thing that Apremeyan can tell you more about. But the idea is that the state is somehow coupled into a microwave photon here. I don't know how it works. You can ask him. But that's the idea. And then you send the microwave photon across your circuit to the other location. And this is called a quantum bus. Very fun names they like to keep. So yeah, that's the scaling part of it, I guess. Otherwise, silicon qubits are quite scalable because the technology is really all developed mostly because Intel and other companies have already worked on it. They have foundries that are working on it. So the real main issue right now is to make multi-qubit gates like CNOTs and stuff, which if they figure out, then good for us, we can start scaling. And one advantage it has over superconducting is that coherence time. We have 1 microsecond. They have patani nanosecond mein kuch. So that is a advantage for silicon qubits. And last thing, I guess these are some groups that you might be interested in for internships and stuff. Mostly this QTech place is in Delft. It is the company was formed in collaboration with Intel, so they have a lot of they got like 50 million funding. So apply there, I guess. And they don't reply. Don't apply there. But yeah. So these are some of the, and these guys did the pioneering, Van der Spijn and Veldhost or whatever. These people did the pioneering works on silicon-based qubits. PETA group is in Princeton. These guys did they have the, I guess, largest array of silicon-based quantum dots right now. They have like 16 or something, I think. So, and they have done some pioneering work on it as well. Tarucha is one guy in Tokyo. He, I think, works on the more material science part of it. Not very interesting. Zumbul is in Basel. He is, again, has done some good work on it and seems like a nice guy, so I put him there. Loss is again Daniel Loss, the guy who made the qubit in the first place. He thought of it. And he's again in Basel, but he's a theory group. So yeah, and in India, I did not write because I didn't have time. India, there is silicon qubits. I know 2 people, I guess. One person is my PI from last year, IIT B mein, Sudasata Mahapatra. Other guy is Madhu Talakulam at ISET Trivandrum. I don't really know anyone else who works in this field here.
So he also does.
Not silicon. Not silicon. So yeah, India mein kam log hai, but people will come, I guess. Let's hope. And yeah, company wise, I told you, Intel is the only one who's backing semiconductor-based qubits. Another company that will come close is Microsoft. They are trying to do topological qubits. I only mentioned them because they use semiconductors, and this was kind of about semiconductors. They try to find Majorana's some hypothetical particle in semiconductors. When you sandwich semiconductors and superconductors together, try to find hypothetical particles. It has been 7 years, nothing has come up, only retractions. So tread lightly. And yeah, I guess we are done. If there are any questions, please let me know.
What gates have been implemented
With
what
silicon?
Yeah, you just mentioned
CNOT with the 2 qubit gate has been implemented. The single qubit gates all have been implemented. 2 qubit with CNOT has been recently implemented for 2 qubits. 3 qubits mein abhi tak nahi. Yeah. Sorry? Toffoli has not been implemented. Anything else?
Dali is there.
Okay. So the next speaker is Apremeyan. He's also from MS20. He'll probably be continuing on what Sahil started, right?
Yeah.
Yeah.
Probably.
Yes. All yours.
Yeah. Okay, thank you. Many people are there, just saying, to the online people. So yeah, thanks to Sahil. So basically the framework will be based on the basics of what Sahil taught. So I'll be adding on to that with a different method. So I haven't shared, sorry. I haven't joined the Zoom meeting. Yeah. Boomer guide. Second, I have joined. I will share. So guys online can see my slides, right? Oh, yes. Password. Yeah, cool, thanks. So yeah, I'll be talking about superconducting quantum circuits as a model for quantum computing. And as I said, I will take less of math and there'll be more pictures. So I hope that will not scare people in the online and offline. Many people are there, as I said. So yeah, I said how to play God 101 because this method is like really scalable and in a sense it's very easy to make stuff here. That's why I have that single line there, just saying. And so yeah, I'll start with what I'm going to talk about. A brief introduction. That's where you all start. And I'll be going back to the basics regarding what I need, the prereqs that are needed to understand superconducting circuits. And then I'll work into the qubit itself. How do you? It's called the transmon. I'll be talking about a little bit about the transmon and what you call the CQED architecture, circuit quantum electrodynamics, if people are wondering what. And of course, you want to do quantum computing. So now I have the qubit. How do I do quantum computing with it? The various protocols and stuff. And of course, the current and future prospects, standard. A brief history of quantum computing. So it started with Feynman proposing the fact that you can't simulate quantum stuff without quantum computers because it gets too hard. Classical computers cannot tackle those kind of calculations. And of course, with that, you went into industries too. You have IBM coming up. IBM started with NMR, then it went to superconducting circuits, and I'll be explaining why. And so that's that. And so apart from the fact that you have these experimental methods, there needs to be a theory that supports this experimental method. You start from the theory, you explain what you need, and then you implement it in a model that can hold this kind of theory. So you had quantum computing methods that is essentially bringing the two-level systems and stuff. And then, of course, doing the algorithms and thereby doing the actual quantum computation itself. So two main types of methods. So first thing is the one Sahil already did, just spin-based, naturally available. You can just use spin, two-level systems, you're happy. And further models are also there. He must have mentioned there is topological, that is trapped ions and so on. All of them are based on the spin stuff. But superconducting uniquely is oscillator based and it's artificial. And I'll be explaining both the words as we move along. So essentially my talk is going to be structured on the DiVincenzo check. So it's like Sahil also had mentioned this DiVincenzo criteria. I find it hard to say this name, but yeah. So you have these 5 criteria that your model must meet in order to make a proper quantum computer. So I'm going to be using that as my backbone in order to explain what and all has happened in superconducting qubits and hopefully convince you that, yeah, this is a good model. So the first thing is a scalable physical system with a well-characterized qubit. So we'll start there. You want to make the qubit. Scalability. I'm just going to give you the evidence of scalability here. We'll come later on to how they actually scale. But yeah, you start with like a few number of qubits on a chip. And now in 2020, it's close to 100. And 2022, it's about 127. IBM recently just introduced their 127 quantum processor, hi-fi stuff. So, I mean, like that shows much promise towards this method of quantum computing, I feel. So that's the scalability part, reference. So now we are going to go back to basics. And by basics, I mean the hydrogen atom. So everybody knows the hydrogen atom. You have the nucleus, you have the electron around it. So this electron is essentially in a potential, a Coulomb potential. And this Coulomb potential is essentially having different levels of energy. And that is quantized. So that's where the quantum part of it comes to use. So this electron can only exist in these energy levels. And as you can see in the picture, those energy levels are being highlighted and it's changing as it moves along. And why is this useful? I will go along checking one more model, which is the quantum harmonic oscillator. And people who have done Chem 102 here must know what this is, I guess. So to people who haven't done much of advanced classical mechanics, this is something called a Hamiltonian, which is essentially a representation of energy. Let's say, I'll just put it there. You want a certain equation which is just talking about energy. So you have here the energy of an oscillator, harmonic oscillator, a classical harmonic oscillator, which is the T square by 2m, which is the kinetic energy, and half m omega square x square, just the potential energy. Well understood, I guess. But now you have the quantum Hamiltonian. So what's going to happen when you go quantum? You expect some complex shit, but it isn't. It's just the same thing, but you put one nice symbol on top of the variables that you have there. It's called a hat. So essentially what happens is when you go into the quantum mechanics of these Hamiltonians, essentially your normal variables become operators. This is something called canonical quantization. So if you have done, again, Chem 102 is the basics that you need for this. These operators are essentially going to act on your wave functions and give eigenvalues as the observables that you see in your system. So your P with the cap is going to essentially act on your wave function, give eigenfunction as your eigenvalue. Again, I hope you guys know what eigenvalues are, and the eigenvalues are going to be the momentum of that state. And same with the position operator. And so now, similarly to the way we represented the Coulomb potential, we write the harmonic potential. And then when we go quantum, it also becomes quantized. And when you do the math, quantum mechanics math, you find out that these energy levels are equally spaced. And the energy difference is h bar omega, standard stuff. So yeah, these are the things to know. You have quantization and these energy level differences are equal. Now I've talked about essentially the quantum mechanics of it. Now we come back to what I want to talk about is the circuits. In analogy to the quantum harmonic oscillator, you have the LC circuit. Okay, let's start classically. The LC circuit is something that you guys must have seen in your electronics course in school, I guess. Essentially, you have a capacitor and inductor. You have charge in a capacitor. It will start moving because of the potential that it has created. The inductor will try to stop the charges from moving, and that is going to act in a certain way that creates a kind of an oscillatory motion of charges around this circuit. So now what we're going to do is, now we are going to take this quantum. What happens? What do you mean by taking it quantum? Is essentially putting it in a way at very low temperatures, making sure that there's not a lot of dissipation. And apart from this, you are going to add these wires as superconductors. What are superconductors? Essentially, as the word suggests, they're superbly conducting. To put it there, they're going to conduct very good at temperatures below the superconducting limit. So essentially what happens is, if you want to go into the physics of what superconducting is, hope I have time. I'll just go take a small detour. Like what's going to happen is in your superconductors, at the limit of superconductivity, you're going to have something called Cooper pairs. Essentially, your electrons, which are naturally repulsing, they are going now pair up. So why do they pair up? Essentially, since they are in a lattice of positive ions, these positive ions, like let's just take a electron in a lattice of positive ions. This electron is going to attract the positive ions around it, and since if that is like at this level of temperatures and with this material, when you have this much amount of positive charge around this electron, you're going to have another electron coming and pairing up with this. And that is going to be traveling as charges in our superconducting circuit. That's a very simple way of putting it. Why only 2 are coming, why can't 3 come? That I am not very sure. I think that has something to do with the math involving behind it. But yeah, so essentially, what's going to happen is you are going to take it to this level of temperatures and less dissipation levels, and you're going to make this quantum. So essentially, what you have here in this graph is you have superconducting phase. Essentially, it's the same as the flux in the inductor. You can just take it like that. The reason why it's phase is because the way current flows through it is similar to a cosine function. So you can just call the argument as a phase. Yeah.
Why did you mention Cooper pair? How is it relevant to this?
I mean, like it is relevant because there is some kind of quantization happening. And these Cooper pairs are essentially this quantized charges which are flowing through your circuit. If I'm wrong, please just tell me.
That does not seem a good argument. I don't need a Cooper pair for quantization. Any quantum particle is going to have quantization.
Right. But
The only case that's relevant is if you say why Cooper pairing leads to a superconducting state and what is a superconducting.
yeah, so his question is, what was the reason I mentioned Cooper pairs? A simple answer to that was because I wanted to explain superconductivity. Maybe not essentially what is related to the quantization here. But yeah, you can just take it from me that effectively at low temperatures and low dissipation levels, this is going to give you a quantized set of energies in terms of what this essentially your the electric fields between the capacitors and magnetic fields in the capacitors are going to get quantized. Only certain energy levels are going to exist in between them. So if you are going to see the potential well here, it's going to be the same since it's behaving exactly like a harmonic oscillator, and energy levels are also going to be the same. So we are going to do a similar thing here, but now with the circuit analogy. With the circuits, the Hamiltonian energy essentially is the energy in the capacitor plus the energy in the inductor. And once you make it quantum, you put the hats on them, you make them operators. And the reason why, I mean, like those two equations are not the same because I've done a little bit of change in the quantum analogy. Essentially, you have Q square by 2m, which is like conjugate to your harmonic oscillator where it's P square by 2m. And then where you have half m omega square x square in your classical harmonic oscillator, here it's half c omega square phi square. Now your mass is, okay, I made a mistake. Q square by 2c. That's not 2m. Really extremely sorry. It's Q square by 2c and half c omega square phi square. So your capacitance acts like your mass. Omega is the frequency of the oscillations of charges, and phi is the flux. So you do the same thing. If you have done Chem 102, you would have done a similar kind of calculation where you create ladder operators. Sorry. So omega square. See, your L comes from the omega square. 1 by LC. 1 by square root of LC. So essentially, you quantize stuff. Essentially, with these operators, you do the ladder operator method of quantizing your energy levels. And this is a small way of putting it. I just wanted to put it there. And the reason why I introduced 0 point fluctuations is because the fact that this becomes quantum. So now what you do is you have made these operators into its conjugate variables in circuit analogies, right? First it was momentum and position. Now it is charge and inductance. Yeah.
Why are we doing this quantization of this equation?
Now we have done quantization of LC circuits, right? It's because now at very low, as I said, we have gone to very low energy level. I mean, like very low thermal levels, a small temperature, where which there's not going to be any dissipation of energies. When you go to this level, the whole circuit becomes quantized. The energy, sorry, it's yeah, it's obeying the same thing that quantum harmonic oscillator obeys, like an electron. I mean, like we'll come to that essentially because you want energy levels. In the end of the day, you want energy levels. Your qubits are going to be energy levels in some manner. It could be spin, as he said. It could be in electrons also in first ground state energy level and this. Now, this is also giving you some set of energy levels. So now I want to make use of these energy levels in order to create my qubits.
What is this Q and phi? Like in a quantum sense, what operators are they literally?
They are the conjugate operators to your xn.
Physical observable. They literally.
You actually you measure the voltage and you measure the current, and then you measure the. I mean, like voltage will give you a sense of charge, and then inductance will be given by half Li square. I mean, like phi will be given by. If I'm not wrong. I mean, like I have forgotten the equations.
So those relations carry forward.
The relations carry forward the same way.
Current operator.
Yeah, current. No, there is no current operator. This is what we look at.
So finally, what we measure?
We measure the charge in the circuit, and we measure the flux given by the circuit through the voltage and currents that we can measure. One leads to the other. Yeah. So as I said, once we one interesting fact is that this also obeys the same kind of relations that P and X do. So you take the 0-point fluctuations of Q and phi, you'll find out that they all multiply them, they also give H cross phi. So that's one thing. Essentially giving you a perfect analogy that harmonic oscillators and LC circuits are the same. The mass spring systems, they work the same, but in the quantum level. But there is a problem in the harmonic oscillators. Why am I talking about this? As Akshay mentioned, we want energy levels. We want to make use of them. Sahil also mentioned. So we want only the first two energy levels, 0 and 1. But then these are like linear energy levels. All of them are of equal differences. The problem is you give some photon of this energy difference between the first and the second state. It might take it to the third state or the fourth state. So we don't want that, because a qubit is just 0 and 1. So that's what we are interested in. So now that's where we get Josephson junctions. I'll just tell you what the Josephson junction is. You take a superconductor, you put an insulating barrier in between them. That is essentially a Josephson junction. Nothing more to it. Essentially, how they make it is they take aluminum, they let it just stay in the air. Aluminum oxide gets formed on it, and at one point it just stops forming, and then you put another superconducting plate on top of it. That's how you create this junction. And sorry, yeah, they will be. I mean, you need junction, it should be the same, or else the lattice things will be different, I feel, at least from what I understand. So this is what it looks like at the nanometer scale from single electron microscopy. And this is how it's realized in circuit. It's just terminology, notation, how they show this Josephson junction. It's that cross there. So why do you need Josephson junctions? I'll come to this later. I don't know why I put this here. Essentially, I'll just give you one more information. You can take two Josephson junctions, make them together, and that forms something called a squid, which I'll come to later. So what do we need these Josephson junctions for? They create the non-linearity that we want. So like you had harmonic oscillators, they were of equal energy levels. But the problem is we don't want equal energy levels. We want something that is changing. And essentially by giving energies only in the range of the first two levels, you'll be able to restrict the qubit or the state that you are interested in into zeros and ones. So that's what we want. So that's what this Josephson junction creates, this non-linearity, and it works in the superconducting regime. So that's why, and it got a Nobel Prize. So all that history is what made physicists choose Josephson junctions. And this is the Hamiltonian of the Josephson junction. I mean, by including the Josephson junction instead of the inductor. So you take off the inductor, put in the Josephson junction, and you create the kind of oscillations. But now it's going to, the potential is now going to be a cosine potential instead of a half x square potential, half kx square potential. It's no more the parabola. So now this new cosine potential that you have is what is creating that non-linearity that you're interested in. So now you have changed the difference in energy levels between the states that are there, and you can restrict yourself to the 0 and 1 state now.
Wait 1 second. Sir. This you're saying it is approximately harmonic oscillator if you go cross by the solution. But then what are they approximating? What like
I am not approximating anywhere. I don't want harmonic oscillator.
So in some range it is still so what range is that what say
I am not very sure. I think since our flux is varying in between,
that's the small
but we are not ready, enclosing our flux in that levels, right? We are still going beyond that. Yeah, of course we are ensuring that. I'm pretty sure they ensure that.
That is why that is not large enough that at the scale of maybe it's not active.
Yeah, so that's where I think I'll be coming to this later on, where you create squids. So that's flux tunable. So that's why what I put in the previous slide. You create flux tunable Josephson circuits with these squids. So essentially you put two of these Josephson junctions together in parallel, and then you can tune the flux that goes through this in order to make sure that they are in the regime that you're talking about.
Also, the only relevance to superconductors is that it can form a state of non-linear.
Not only this, your bias is superconducting. The fact that before this, the LC oscillators were still working in the quantum regime, right?
Okay, you don't want you want resistance
Yeah. Yeah.
And you want some non-linear.
Yeah.
Those are the only two things.
Two things that you are using.
When you go to coupling with microwave, which doesn't, you can't go to the other thing. You need some. Okay. Like you have.
Can you list the properties of a superconductor?
Yeah, I think
if you require. I don't care that you're calling it a superconductor.
Maybe as I go, we'll be coming to them one by one.
Make a list of it.
Yeah, sure. So yeah, now you create your transpond qubit. Essentially what happened was, we took out the inductor, put this Josephson junction here. We have created a transpond qubit. With respect to the picture here, you have these two metal plates that acts as your capacitor. And then in between you have the small yellow thing, which is essentially your Josephson junction that creates the non-linearity. So you have created your qubit. Now, one more thing that if I go back, go to the Vincenzo criteria, is you want scalable physical systems with well-characterized qubits and ability to initialize a state of qubits to a fiducial state. So in terms of initialization, you need some kind of control over your qubits. So that's what I will be doing now. I don't know why I put that later. So what you're going to do is, in terms of interaction, you need some way of making to interact with your qubit, right? From you're in the environment, you've made the qubit there. Now you have to make sure you can interact with it. So what you do is you have your transpond here. That's a nicely drawn diagram of the transpond, which is the capacitor and the Josephson junction. What you do is you couple it with a capacitor here, and then you send it to whatever voltage signal that you're sending. So that's how you essentially communicate with your transpond qubit that you have here. And yeah, you essentially send these photon signal through this external circuit that you have, which you have coupled with your capacitor. So the one problem that you face is, once you have coupled with the capacitor, the reason why you couple it with that capacitor is because you want some kind of control over the kind of signals that you're sending. And but the problem that arises at the same time is you lose that non-linearity. So now once you create that coupling, your energies change, your Hamiltonian change. So once that Hamiltonian change, this non-linearity also changes. And essentially this graph, what is telling you is, depending on the charge in that coupled capacitor, how are the energy levels changing? So green is your 0 level, yellow is your first level, and you have the purple is the second level. So these things are changing. And the problem with that is for small changes in your coupled capacitor, you will find quite a change in your nonlinear, in the differences between the energy levels of whatever systems that you're looking at. So that is a problem because you will always have some kind of leakage of charges which are happening, and that will completely change your Hamiltonian, and the energies that you're sending in as signals will not quite take it from 0 to 1 because now your energies have changed depending on the coupled capacitors charge that you have. So any noise would disturb the system too much. So that's why you work in something called a transmon regime. Essentially what you do is you increase the in-circuit, the capacitor which is there inside the transmon. You change the capacitance of that capacitor in order to make sure that these energy levels get sustained like that. I mean, like, I'm pretty sure, I don't know, it has to do with the math, I guess. I don't know exactly how this changes, but it changes when you take a very large capacitance. You will find out that these energy levels start becoming straight and it doesn't vary over with the charge that you keep in your coupled capacitor. So one problem that comes is it almost becomes like of the same energy levels, but it's not too close. So you can still work in the nonlinear regime. So now we go back to our DeVincenzo check. We have done the first two. Now the third one is just looking at it with high decoherence times. You need these qubits to have high decoherence times. And for that, I just have this graph. Essentially, you have different kind of qubits which have come over time. And as you can see, so here I'm happy that Sahil already mentioned what these T1 and T2 times are. So essentially, you see the way they have the superconducting qubits have evolved over time, and they're giving much higher T1 and T2 times. I would do another DeVincenzo check. Fourth one is universal set of quantum gates. So to do that, you need this kind of coupling that has to happen. You need two qubits to interact. You need to create multiple qubits, not only just one. So in order to do that, you do it with a coupling capacitor. And the reason all why this works is can be seen by looking at the Hamiltonian that this kind of a system generates. You look at the contribution of this coupling capacitor, what it does. And when you do the calculation, it doesn't matter. You can still maintain the qubit levels of each transmon. And furthermore, it can help in applying, I mean, like once you have created this, you just connect it to external voltage signaling source. It will send in stuff. And based on the kind of gates that you want to do, you know what kind of pulses you have to send. You just keep sending them through your external circuit. And that's what's going to essentially do the quantum computation of your transmon qubits. And in terms of entanglement, you have to send in certain kind of pulses, which in a certain sense, whatever one transmon receives, it absorbs and scatters, and this scattered signal is sent to the next transmon. And that's how you create a certain sense of entanglement between two transmons. I think you can see more about this in this 2 qubit gates for quantum computation. Now our fifth Vincenzo check, measurement. So last thing is measurement. In terms of measurement and readouts, one would just think like, okay, I'll send in a readout signal. It will go, take in the information from the transmon, and whatever is reflected will carry information about whatever the state the transmon was in. But the problem with that is you lose the qubit information because once you do the measurement, that's lost, right? It is when gone into the 0 state or 1 state. That's what the measurement is about. And there's another problem, which is it could also, the information that you have could also leak through this coupling capacitor that you have. So these are two problems with direct monitoring of this measurement. So instead, what they do is, it goes on to 1 state. That's measurement, right?
Yeah.
Oh, it goes now. You can't use that qubit anymore. Again, you have to initialize it, wait for it to go back to 0 state. All that, I don't want to do that. So what they do is you just want the information from it without actually losing its state itself in which it's existing. So for that, they just add one more thing, which is LC oscillator. So essentially, this is a much more non-destructive way of doing it. Essentially, and what you can say is this has been written as a cavity. The reason why it's given as a cavity is because there's one more way of doing it. It's essentially taking this qubit, keeping it in a cavity, actual cavity, keeping it in a box, and then sending in photon pulses of certain range, which is in resonance with this cavity. And then using that, you can get the readouts from that signal and then make your measurements. And essentially, and one more thing is the way you can visualize this. Yeah. So the way I see it is, in a sense, sorry, I am not, you're just taking the information in the sense, maybe I'm not very well thorough with the fact of what's exactly, what kind of signal is coming out from that. But essentially, this is a much more non-destructive way of doing this. That I can tell you that.
Your qubit is in some superposition.
Ah.
You do your measurement.
Yeah,
You get 0 or 1.
you get 0 or 1.
But that is still in the same.
That is
So
still-
you can keep taking readings from
I
that.
can still keep taking readings.
Without verifying.
Yeah,
That's kind of against.
that's kind of against.
Isn't it natural that for us? I mean, with what?
I think maybe I'm not very well thorough with the kind of measurements that are happening, but I can just tell you it's a much more non-destructive way of doing it.
But I'm saying it should be.
It should be destructive. Probably I have to give it my better read regarding this. So essentially, that's what happened. You send in a readout signal, and yeah. So depending on the state in which this qubit is in, you will get a certain readout reflection, which you measure, and then which will collapse into 0 or 1 depending on the voltage. Yeah. So that will give you a sense of whether it's in 1 now, or it's collapsed to 1, or it's in 0.
Can you like elaborate on what the photon is?
Which photon?
Oh, yeah, you mentioned in the previous slide. You're saying you're coupling the qubit to a cavity and the cavity to a
Yeah,
photon.
to a signal. Essentially,
Calling
what
it
is
microwave?
it's a microwave. It's a microwave. If you're calling it a photon, yeah. So yeah, this is your final product. So this is where what you said comes in. Essentially, instead of having just one Josephson junction, you have 2 Josephson junctions, and then you look at the flux through both of them, and you have the coupling capacitors there, and then you have the resonator, and you have the signal which is coming outside. Yeah. So VJ is the signal which you are sending in. The resonator is in red, and the transmon is in blue and light blue. I mean, light blues are things which are connected. So regarding investment and industry, I hope some of you guys know what this reference is. Essentially, it's Jerry Maguire shouting, "Show me the money." So you have companies like Google. So I'm talking about only superconducting qubits. The companies which are into this are Google, IBM. Those are like other companies, computational companies, which have also diversified into quantum. Now you have Rigetti and D-Wave, which are like purely quantum computing companies. And essentially, there's a lot of money in the industry. So you can definitely get into it, I guess. Regarding labs, major lab in India is Vijay Raghavan's lab in TIFR, beautiful lab for superconducting. And in IISc Bangalore, you have Balatithya, Mibor Singh. The thing is, in order to create these very low temperatures, you need something called a dilution refrigerators. Not many institutes have that. That's why you have only top-notch institutes in India having this equipment, and therefore where these kind of research is happening. Huh? We have one. I don't know what's being used for. And in terms of outside, it's just endless. You have Yale, which is like the place where superconducting itself started. You have these 3 very top-notch people in this field. You can look at their papers. It's very interesting. And Walraff, also one of the pioneering researchers there. He's in ETH Zurich. Blaise, he's more at the theory side of quantum computing. And rest of them you can just Google. So major research, which not many speakers before didn't tell you, is this book. This is the Bible, and tell you that they celebrated their 10-year anniversary, I think like 8 years ago, or I don't know, a decade ago. So the field is quite new, and this is the textbook that you have for this field. And essentially, if you give this a read, I think it's more than enough to understand quantum computation and information. And acknowledgements, most of the things that I've taken from this, I can maybe send it out. And with that, I think I will end my talk. This is one thing that I have. Yeah, sure. If I know, I will answer.
This just a risk platform. What are the disadvantages?
I didn't mention the disadvantages. Mostly it's just based on engineering only. You want high decoherence times. You don't want to lose information. All that kind of stuff only. From what I understand,
That's a general problem everywhere.
there's a general problem everywhere. But the thing is here you can engineer stuff based on what you want. There you have to work with what nature only gives you.
Noise, error correction.
Error correction is also there, which is also there in spin qubits.
Spin qubits don't have that. But spin qubits are not scaled.
They're not scalable. Yeah, that's where your engineering thing comes into favor.
So what people are saying, I mean, like this word scale, they're trying to do hybrid qubits. They do part of it is like the memory part is, I don't know what memory part is. The memory part is the semiconductor base. Computing part is
No superconductor.
What is the problem for spin?
Scalability. Like, I mean, see, it is scaled, but then you can have 500 qubits, 500 well on one silicon chip, you can make an. That is not the issue. The issue is that how do you make them communicate with each other? How do you make them? You can have single qubit 500 bits into the use. Okay. So
So here you can do that.
here you can do that, but with a lot of error.
Yeah. So that's where error correction.
Both are equally bad.
I mean, like, thing is here, in terms of scalability, this is much better.
Otherwise, I don't know what your unit is.
And I think because we break it, say minus better.
No, in terms of scalability, and you can engineer stuff based on what you want. I can change flux way I want. I mean, like, but you can't create much, right? You can only create 2 or 15 or something. I mean, like, T-Wave has more than like 1,000 or something, if I'm not wrong. But they do measurement based. There's one more thing called measurement based quantum computing, but that's a whole.
Five is 700.
Yeah, I can make math.
But it was fast. Yeah, I think.
So,
Yeah.
personally, as a researcher, how do you pick which platform is more promising? Did you?
Well, for me, it's more like interest. The reason why I feel this is better is in terms of understanding. I was always interested in electronics, and I want to do something with quantum computing also. This seemed that the only thing and made for what interest I have. That's how I saw it. And based on the industries that you have, most of, I mean, like, this is how it started. Money is going in everything, but in spin, I'm not sure. How, I mean, like, Microsoft is there.
No, not as much as superconductor.
Not as much as superconductor.
So it's not promising as per the industry.
No, because it's like a link effect. No, IBM like another statistic funding. Then everywhere else is also funding.
In terms of marketing, also they did a better job, I guess. So yeah, this is what.
What other platforms are there?
In terms of circuit based, I think this is the only thing.
And generally overall, or
Ramdine is very prominent, but not mentioned because of.
Ion Q is.
The basic idea is they put some electrostatic potential and put one ion in between, and then pulse it with lasers to change its spin speed.
that's similar to yours. No?
Yeah.
Similar to my.
One more thing is photonics. It's the same. But if you want something different, there is photonics where Xanadu is doing some stuff.
Photonics is not.
It's just they don't know interact much, so I don't know, but still there's a lot of funding. Communication, it's very good, yeah. But Xanadu, recently, I think they got some $50 million or something from the Canadian government to do this quantum computing with photons.
Okay, let us start and then find.
Yeah.
So, what about topological? That's like
That is the main issue with their.
We'll just do away with the. Does anyone have a question from Zoom?
Two people are.
Okay. Okay, no. So
Yes, no.
we'll meet again tomorrow for Abhasu's talk. No, we'll be here tomorrow. Yes. See you tomorrow, Laksha.